Hey, good morning, everybody. This is Mr. Ainsworth, and I mean good morning because it is 6 o'clock in the morning when I'm doing this here. I don't always make videos in the morning, but here we go. We're going to launch into a really cool topic in graph theory called Euler circuits and Euler paths, coming from the main man Leonard Euler. So I'm going to start off with a true story here about how graph theory was invented and where it all originated back in the 1700s or the 18th century here when Leonard Euler was around. See, he was born in 1707 and he died in 1783. That's the 18th century. And back then, in what was called Prussia, now Russia, there was a city called Konigsberg, but today it's called Kaliningrad. And what happened was that there was this famous town called Konigsberg, and in this town there was a river called the Pragel River. And let me see here. Yeah, there was the Pragel River flowing around and in through Konigsberg in what was called Prussia at the time. Now this river flowed through the city and it went around two islands here, B and C, and the names of them, one is unknown, the other one's Nelpov or something like that. And it flowed around them, and in between the mainland and the islands, there were seven bridges. So this is often called the seven bridges of Konigsberg problem because this is where it originated. But the story goes like this, okay? The question is whether a person can walk in such a way that he will cross each of these bridges once, okay, but not more than once. I was told that while this I meaning Leonard, okay, I was told that while some denied the possibility of doing this and others were in doubt, no one maintained that it was actually possible. So Leonard Euler, when he heard of this, began to formulate the general theory, which was solved, or which solved the particular problem called the seven bridges of Konigsberg. And he pretty much invented the new field of mathematics called graph theory. Basically, what he did was he reconstructed the problem. He took the map of the city here and simplified it to something like this, and he kept on simplifying it. And he called the four regions the right bank A and the left bank here D, and then the two islands they were B and C in this drawing here. And he thought of these bridges as ways to get from one point to the other, and hence the arrows here. Way number one goes over bridge one. Way number two, this direction here was way number two to get over bridge number two to the main island, and so on. And he kept on simplifying it, and so in the end, he ended up with 4 points representing the four pieces of land, the right bank, left bank, and the two islands here. So you got four pieces of land. So therefore, 4 points. So let me draw them here. So this could be, point A, and then point B, and then point C, and then point D, roughly. Okay, so 4 points representing the four uh, pieces of land. So I'm going to draw them in red, right? And then he drew these arrows, which are now called edges, to represent the ways going across each one of the seven bridges. So there are seven bridges or seven edges because there are seven bridges. So here, way number one. So one here, two here to get from point A to the main island, and then main island down here to the left bank or um, the other land piece here. There's only one bridge to go from island to island, so we only drew one bridge here. And then to go from this island down here to the left bank or the lower landmass, there's one bridge right there, bridge 7, and then up here, bridge 4 to get to the upper landmass or the right bank. So this famous diagram right here with seven edges, okay, 1, 2, 3, 4, 5, 6, 7. He used to represent the situation in Konigsberg. Okay, so the bridges are in blue. Bridges are in blue here. All right, and the land masses are in red. Land masses are in red. So he simplified it, and this process of simplifying the problem as a set of points called vertices and edges or curves, which are in blue here, was something totally radically new. No one before Euler has done this. He took a problem, modeled it with 4 points and seven edges, and then from this he deduced that it was impossible. And because of that, graph theory was born. Okay, this is a graph, a typical graph in graph theory. Graph theory uh, was born back in the 18th century. Okay, back when Euclid or Euler, excuse me, Euclid's another guy. Back when he was born, back in the 1700s. Just because of this famous drawing, and later on through the chapter here, we're going to learn the theorems that Euler came up with to prove that this was not pretty much traceable. Okay, we've done the universal tracings as an intro activity. Well, there's no way in the world you can trace this without lifting your pencil. All right, which was basically the same problem as what they talked about back in Knigsberg back in the 18th century. You could try it all day long, but it's impossible. Okay, so uh, so in this chapter, we're going to be talking about a couple main things. We're going to be talking about Euler paths. We're going to be talking about Euler circuits. We're going to be talking about routing problems, and we're going to investigate, what is the optimal route? What is the best route, the cheapest, the fastest, the shortest route or path or circuit in particular problems as we go through the chapter. So there's a lot of things to do. There's 7 essential questions here that we're going to answer throughout the chapter, so you can read those through if you like, and we'll address those per section here. And then we have a lot of vocabulary to go through, so we'll address all these different vocabulary terms as we go through. So by the end of the chapter, you'll be familiar with all of these right here. The first lesson, sections 1 and 2, is basically an intro lesson. It's where you get used to the vocabulary and the nuts and bolts of graph theory. Okay, how to dissect a problem and how to determine its edges, vertices, edge set, the degree of the vertex, and so on. How do you see if two graphs are the same or isomorphic? That's what you learn in sections 1 and 2. So we're going to get right into it. This is seen in management science. That's what it's called today. And basically, it's ways to find efficient ways to organize and carry out a large number of complex tasks that do not often appear possible to make optimal. All right, which means best, all right, decisions. So how do you make the best or optimal decision, and how do you be efficient in solving a problem that involves a large number of tasks? How do you do that? Well, routing problems are like that, and they're used to find ways to route or send the delivery of goods and services to assortment destinations. FedEx is a good example. UPS is another good example. The United States Postal Service. These are all good examples that of companies that have to deliver many, many different things to many, many different locations. All right, even the commercial airlines. Okay, this is another good example uh, of companies that actually have big jobs to do, and that they have huge routing problems to solve. Okay, to get from East Coast to West Coast, to minimize the amount of gas used and decrease the time, minimize the time traveled and the distance traveled so that the gas can be reduced, is a huge graph theory problem. Okay, nowadays it's done with computers. However, the basics behind it are routing problems. Okay, so there in this chapter here, there's 2 basic questions that we need to answer. One is the existence question, which is a route possible? And most of the time it is. Okay, so if yes, all right, the number 2, the second question is the most important question. If there are multiple solutions, which they usually are, okay, if there are multiple possible routes, all right, which route is optimal? Okay, which route is optimal? Okay, I'm talking best. Now, when I say optimal, okay, I'm referring to this. I'm referring to either the shortest route. What's the shortest? What's the cheapest? Okay, and something in that category right there. So we're always looking for the shortest route because we're trying to minimize either time, cost, or distance, and to maximize our profit in the financial situation, whatever the company may be. And there's always there is something called the exhaustive requirement that we're going to be looking at through some of the problems here throughout the chapter, and that's a fancy terminology for something actually quite simple. The exhaustive requirement means that the route, okay, must go everywhere. All right, I mean to all destinations, to all destinations. Now the most common example that you guys can be familiar with is the postal service. Okay, the mailman has to go to every single house on the route. Otherwise, he's going to upset one of the destinations, the people at the destination. Because if he skips your house, you're not going to get your mail, right? So he has to fulfill an exhaustive requirement because he must go to every single house on his list, kind of like Santa Claus. Okay. All right. Now let's get through the nuts and bolts here. All right, a graph is a picture consisting of dots, which we're going to call vertices. Okay, there's another name for them. We also call them nodes, N-O-D-E-S. And lines are curves, which we're going to be calling edges. All right, we have to say line or curve because it's not always straight. You have to get that in your head and get used to that in graph theory because it's totally different. Okay, it's a little counterintuitive um, in respect to algebra 1 and 2 and pre-calc that you're used to. Okay, we're not looking at the same graphs on the coordinate plane that you're used to, so you got to change your thinking a little bit. This type of graph represents an area of mathematics called graph theory, obviously, and it's different than graph functions on the coordinate plane. That's what I was just saying. The formal definition of a graph is a structure that defines a pairwise. That's a keyword, pairwise. All right, relationship, which are edges. All right, with a set of objects called vertices. Okay, and it's stated that x is related to y if and only if xy is an edge. Okay, well, let's draw a picture of that. Let's say this is x and this is y. Okay, if you have either a curve, a line, or an edge, it doesn't really matter how it's shaped, joining two vertices, that's an edge. So this is edge as xy. You have to keep in mind though that it may look a variety of different ways. So if the edge looks like this, okay, I don't know how long it is. I don't care how squiggly it is or curved it is. All right, it's still an edge xy. So the shape of the edge does not matter, is what I'm saying. All right, the fact that it's joining x and y, that's the only thing that matters. Where x and y could represent two houses, and this red edge here, the edge in red, could just represent a let's say a street to get from x to y. Okay, it could be as simple as that. So what we want to do first is get used to the different components of a graph. Okay, the vertices, edges, loops, multiple edges, and isolated vertices of a graph, and get used to the common lingo so that we can talk about different graphs when we model them. All right, so let's start off with vertices here. We're going to take this simple graph and understand that vertices are just points, okay, dots, okay, or nodes, all right, on the graph. Okay, and so in this case we have 5 of them, A, B, C, D, and E. So I'm just going to list them here. So A, B, always list them with a comma, right? A, B, C, D, and E. We have 5 of them. Okay, the edges, well, they're lines or curves connecting 2 points, right? So lines, okay, but I'm going to also say curves because guess what? It doesn't have to be straight. Like look at this one here. This is a curve right here. That's an edge. And E to D, well, they've got a couple edges right here, and they're not straight either. So I have to say lines or curves connecting, all right, 2 points. So let's list them, okay? I'm going to put this in red so we can see this easily. So I see AE here, edge AE. AD is another edge. A is connected to D, so that's another edge. And then AB here, third one, AB. So A is connected to E, D, and B, so there's 3 edges there. E is connected to D twice, so there's 2 edges here, and we need to list them twice, all right? ED twice. ED. So we have 2 edges. Those right there in red, this one here, and this one here, those are called multiple edges. Okay, when two vertices are connected by more than one edge, they're called multiple edges. So let me write that down. When 2 vertices are connected all right, by more than one edge, you have what are called multiple edges. And so here, ED, come on, ED is called a multiple edge because obviously there's more than one edge right there. Okay, there's one, two right there. All right, so you have to list them twice in the list. We're not done yet here. Check this one out. This is a weird edge right here. This edge right here in blue, so B goes from B, starts at B and ends at B. All right. Well, guess what? This the sixth one right here, and that's called edge BB, and this is called a loop. All right, and it has a name, BB. So you always denote each edge with two letters, where it starts and where it ends. And since this edge starts at B and ends at B, we call that BB, and it's called a loop. All right, so a loop, which we have one of right here, and we have two multiple edges. A loop is an edge connecting a vertex back to itself. So let's write that down too. And an edge is a loop is an edge, excuse me. A loop is an edge that connects a vertex back to itself. All right, and so the example that we have is edge BB. So we have one loop, we have two multiple edges, or one multiple edge, but it's twice, right? And then we have three additional edges here. So we have actually 6 edges total. So I'm going to put 6 up here. 6 edges, 5 vertices, one loop, multiple edges. And this thing right here, this is called an isolated vertex right here. Why? Because there's no edges. It contains no edges, and it's not connected to any of the vertex. So we call it isolated. It's kind of like an island in the sea. Okay, it's an isolated vertex. All right, and vertex with any vertex with no edges. That should make sense, okay? So it's isolated, it's like an island. And there you go. And the last thing I want to talk about right here that we're going to be using in future lessons is what's called the degree, okay? So I'm going to add that in. So write this down. Degree, okay, of a vertex. We're going to be dealing with that. You heard me talk about it a little bit the other day when we talked about unicrystal tracings, although I didn't use the word degree. All right, and the degree of vertex equals the number of edges. All right, the number of edges that end or come into a vertex. Okay, that end, okay, or come into a vertex. So let's highlight that. This is an important concept. We're going to be using this a lot. So the degree of a vertex is the number of edges that end or come into a vertex. So for example, right here, there's for A, vertex A here, there's one edge, two edge, three edges that come into vertex A. So think of A as like a house, for example, and there's three streets, let's say, and these edges represent streets. There's 3 streets leading into this vertex right here, or to this house. So that we say that the degree of A is equal to 3. All right, DEG stands for obviously for degree. So the degree of A equals 3. Right here, the degree of E is equal to 3 as well, because there's 1, 2, 3 right here. 3 edges coming into E. So the degree of E equals 3. I'll talk about the loop in a minute. The degree of D, there is 1, 2, 3 edges leading into D, so the degree of D equals 3 right here. And the degree of B right here, let me see, there's 1 street coming into B. Let's think of B as a house, let's say. There's 1 here coming into B here. And there's another way to get into B. It's over here, over here. So the degree of loop we're going to define as 2. So this is really degree 3 here. There's 3 ways to get into B. Okay, this way, and this way. All right, so the degree, okay, of B, all right, is equal to 3. There we go. So that is another important concept in graph theory too as well. So add that into your notes. All right, there is a lot more, so let's get some practice here. So let's go into the next page here and have you guys give it a shot here. All right, so in each one of these graphs, we want to figure out the vertex set, which is just the set of all vertices. The edge set, which is just the edges labeled with by two vertices, right? This the listing of all edges, and then we want to list the loops, and we want to count how many of each we have in the set. So I'm going to illustrate one more time on problem number 1 here, and then you can pause and play the video and do graphs 2 and 3. That's what you should be doing, okay? You shouldn't just be copying down from me. You should be we're working with me in the video, pausing and playing, try something, okay, and then play the video as we go. Basically, pause and play. All right. Excuse me there. I just had to take a sip of coffee here because it's 6:25 in the morning. All right, here we go. So vertex set. Well, there's 1, 2, 3, 4, 5 vertices, right? So A, B, C, D, and E. This stuff's not that hard, okay? So you got 5 vertices there. Now the edge set, let's count them as we go. All right, C, A, B right here. I'm going to just list them as I label them. So A, B, A, E. This is a good way to keep track of everything right here. A is not connected to anything else, so we move on. So B, E. All right, B, B, D. This is D right here, okay? Little typo there, should have been D really closer to the vertex itself. Okay, so BD, BC, and then CE, and then D back to itself. This is your loop right here. So DD. So let me see, that's 7, and then 8 here, DE. So I see 8 right there, and let's see here. So we have 5 vertices, 8 edges. We have 1 loop, and that's DD. Multiple edges, I don't see any. There are no any two vertices that are connected by more than one edge. So none right here. 0, and there are no isolated vertices. So when there are none, you just write down none. Or you can put down, I guess, NA if you like. Okay. All right. So pause and play through the video here and give graphs 2, 3, and 4 a shot. And let's see how it goes. Okay. Okay. So I assume that you already tried this. So a vertex set. So we have M right here. So M, N, O, P, and then Q, and then R. I like to go alphabetical right there. And then edge set, here we go. So QM, that's 1. QP, so notice how I label them as I go and make it simple. All right, QO, I like to list things in order. And then PM is 4. And then PO is 5. And then I have, let me see, MN twice, so 6 and 7. So MN, MN, there's your multiple edges. So MN is a multiple edge. And no loops. I don't see any loops. Okay, and I see 1 isolated vertex. Okay, so we have point R as an isolated vertex right there. So I have the only 2 multiple edges I see are right here. Why? Because these 2 vertices, M and N, are connected by more than 1 edge. So they fit the definition, right? No multiple edges anywhere else. Okay, so let's go through graphs 3 and 4. So go ahead and pause the video and give graph 3 a shot. Okay, let's check your work. Okay, so on this one here, we have A, B, C, D, E, and F. So A, B, C, D, E, and F. 1, 2, 3, 4, 6 vertices right here. And we're going to label them as we go. So the loop here, AA, is the first one. So I'm going to list it first. And I see AB, AB, A is connected to B. And then I see BC. And then I see CF twice. So 4 and 5. So CF twice. CF, CF. There's your multiple edges right there. CF, that's one multiple edge, because it's two vertices that are joined by more than one vertex, excuse me, more than one edge. And then I see BD here, and that's 6. DF, that's 7. And then 8, 9, and 10. So I have to list DE 3 times. So DE 3 times. DE, DE, and DE. Okay, there's another multiple edge right there. Why? Because DE is connected by more than one edge, right? So I see multiple edges here, here, and here. Multiple edges. And let me see, any isolated vertices? Oh no. Okay, none there. All right, in graph 4, I'm going to assume that you did that already. If not, pause the video. So here we go, vertices. UVW, so UVW, X, Y, and Z. Okay, edge set. So here we go. So UU, UZ, UY, that's 3, 4 ZY, ZX, that's 5, and 6 YX, and the other loop XX, so that's 7. So XX here, so you have 2 loops. So you have loop here and you have a loop here. So there's 7 edges, there's 1, 2, 3, 4, 6, 6 vertices, there's 2 loops right here, loop UU, this one, and loop XX, and let me see, no multiple edges, and 2 isolated vertices, V and W. Okay, and there we go. That's how it's done. Okay. So what we're going to do now, and what you're going to do now, actually, is reverse the process. Okay. I give you the edge set and the vertex set. You guys come up with a graph. Okay. And so what we're going to do is we're going to split the video here. I'm going to pause here and split section 5.2 into 2 videos so I can take a break here and have you guys go through this in my next lesson. So if you need help with this, go ahead and go to my website and take a look at the second half or part 2 of section 5.2 video here. And basically it's a reverse process. I give you the vertex set and the edge set, you come up with a graph. And what's cool about these is that there's multiple graphs possible, okay? You just got to make sure they're the same. Okay, this is Mr. Ainsworth. I'm out of here. I'll see you in my part 2 in lesson 5.2 later.